Python's iteration protocol distinguishes between iterables and iterators. An iterable is any object capable of returning its members one at a time, such as lists or strings. An iterator, however, is an object representing a stream of data produced by calling the iter function on an iterable. Understanding this distinction is crucial for mastering Python's iteration mechanisms. Python's iteration protocol is crucial for efficient data handling. An iterable is an object that can return its members one at a time, while an iterator is an object with a state to track its position during iteration. Iterators implement the _next open parenthesis close parenthesis method, allowing seamless traversal of data structures. An iterable is a Python object that allows iteration over its elements one at a time, such as lists, tuples, strings, and dictionaries. It must implement the _iter method, returning an iterator. For example, the list 1, 2, 3 is an iterable enabling sequential traversal in a loop. An iterator implements both iter and next methods, maintaining an internal state to track its position. It returns the next item on demand via next and raises a stop iteration exception when the sequence is exhausted. This mechanism allows for controlled, fine-grained access to elements in a sequence. An iterable is an object that can be looped over, calling _iter to produce an iterator. The iterator, acting as a stateful cursor, uses _next to traverse and yield elements sequentially. This mechanism efficiently manages data retrieval, maintaining position and controlling access to each item in the sequence. In Python, the iter function calls _iter_i to create an iterator from an iterable, like a list. The next function then uses next to access each element sequentially. For example, iterating over my list yields 10, 20, and 30, before raising a stop iteration exception when elements are exhausted. The iterator protocol is fundamental for creating custom iterators, allowing developers to define unique data traversal patterns. By implementing the _iter__ and next_ methods, objects can seamlessly integrate with Python's iteration mechanisms, enhancing control and flexibility in data handling. This protocol ensures consistent iteration across various data structures, supporting Python's for loops and comprehensions. The iterator protocol in Python involves two key methods: _iter, double parenthesis, and _next double parenthesis. _iter, double parenthesis, returns the iterator object itself, enabling iteration. Next retrieves the next item, raising stop iteration when done. This protocol seamlessly integrates with Python's for loops and built-in functions, standardizing iteration across various data structures. The string iterator class demonstrates a custom iterator by implementing _iter and _next methods. It maintains an internal index to track position, returning each string sequentially. When the sequence is exhausted, stop iteration is raised, ensuring seamless iteration over the provided list of strings. Using the string iterator class, we can iterate over a list of strings. The for loop invokes iter and next methods, printing each string in uppercase. This demonstrates how custom iterators streamline iteration, automatically handling state and termination with stop iteration. Custom iterators allow for specialized iteration logic, enabling conditional skipping, filtering, or transformation of elements. They can generate infinite sequences, providing unlimited data streams without excessive memory use, perfect for mathematical sequences. Additionally, they facilitate navigation through complex data structures, such as tree traversals or graph explorations, using custom algorithms. Generators simplify iteration by using the yield keyword, allowing values to be produced lazily. This approach eliminates the need for explicit state management, making it a memory-efficient alternative to traditional iterators. Generators are particularly useful for handling large datasets or streams, as they compute values on demand, conserving resources. A generator is a function using yield to produce values over time, unlike return. Python handles the iterator protocol for generators, preserving local variables and execution state between yields. This lazy evaluation computes values on demand with next, optimizing memory and processing resources. A generator function like square, generator n, uses yield to pause execution and return values one at a time. Local state is preserved, allowing the function to resume from where it left off with each next call. This process continues until the function completes, efficiently managing memory and processing resources. Generators offer a simpler syntax with minimal boilerplate, managing state automatically via yield, and are memory efficient by computing values on demand. However, they cannot be reused once exhausted. Traditional iterators require explicit class definitions and manual state tracking, offering more control and the ability to implement complex logic. Generators are iterators, but not vice versa. Generators use a suspension and resumption mechanism, maintaining execution context across calls. When next is invoked, execution resumes until a yield statement is hit, returning a value. This process continues until stop iteration is raised, allowing for efficient lazy evaluation of sequences without storing the entire dataset in memory. Generator expressions offer a compact syntax using parentheses, like x times x for x in range 5, similar to list comprehensions but creating a generator. They generate values lazily, providing memory efficiency, especially for large datasets. For example, squares equals x squared for x in range 1 million efficiently computes squares without memory overhead, ideal for partial results. Advanced generator concepts extend beyond basic iteration, enabling efficient handling of infinite sequences and scalable data processing. They allow for composing iteration pipelines, crucial for processing large datasets. Generators maintain a near-constant memory footprint, making them ideal for building systems that require efficient data handling without the overhead of storing entire sequences. Infinite generators like the Fibonacci sequence allow for continuous number generation without storing the entire sequence using constant memory. This efficiency is crucial for handling large or infinite data streams. Unlike lists, which grow with data, generators maintain a near-constant memory footprint, making them indispensable for scalable data processing. Chaining generators with yield from simplifies delegation by passing control to another generator seamlessly. This syntax transparently forwards values, exceptions, and handles stop iteration automatically, resulting in cleaner code. It enhances composability, allowing the construction of complex iteration pipelines from simple generator functions, eliminating the need for explicit loops. Synchronous iteration uses iter and next, blocking execution while waiting for values. Asynchronous iteration with iter, and next allows concurrent operations, ideal for network data streams and real-time processing. Asynchronous generators, using async def with yield, enable non-blocking iteration, essential for I/O-bound concurrent applications in modern Python async programming. Reading large files efficiently is crucial. Using a generator, like in the read large file function, allows processing one line at a time. This approach maintains constant memory usage, enabling handling of files larger than available random access memory. For instance, processing a 10 GB file with minimal memory footprint is possible, as only the current line is stored. Avoid reusing exhausted iterators. Once stop iteration is raised, create a new one. Handle stop iteration by catching it or using a default with next. For large data, prefer generators over list comprehensions to save memory. Document generator behavior to ensure clarity on reusability, side effects, and initialization needs. Iterables serve as data containers, implementing _iter, double parenthesis, to provide an iterator. Iterators use _next double parenthesis to traverse data while maintaining state. Generators simplify this process with yield, enabling lazy evaluation. These mechanisms are crucial for writing scalable, memory-efficient Python code, essential for data processing, stream handling, and algorithm implementation. Develop custom iterators and generators for practical applications, starting with simple sequences and advancing to complex structures. Experiment with generator expressions, yield from, and infinite sequences to test memory efficiency. Explore asynchronous generators for concurrent applications. Utilize resources like RealPython, DataCamp, and Python's official documentation for deeper insights.